The minimum pressure and the temperature in an Otto cycle are 100 kilopascal and 27 degrees centigrade. The amount of heat added to air per cycle is 1500 kilojoule per kg. Determine the pressures and temperatures at all points of air standard Otto cycle also calculate the specific work and the thermal efficiency of the cycle. For a compression ratio of 8:1, take CV of air is equal to 0.72 kilojoule per kg Kelvin and gamma of air, as we know, it is 1.4. The solution to this problem is obtained like this. Let's draw the Otto cycle on PV plane. He has given P1 as 100 kilopascal, which is of course atmospheric air pressure, and T1 is 27 plus 273, that is 300 K. It's also atmospheric temperature. Now let us obtain P2. Given that compression ratio R is 8 for the cycle, I would obtain P2 first. P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma. Therefore, P2 is equal to P1 into V1 by V2 whole power gamma. This is equal to P1 into R to the power of gamma. We shall calculate P2 in kilopascal because P1 is 100 kilopascal into 8 to the power of 1.4, that results in the P2 in kilopascal. And the temperature T2 also could be calculated like this. T2 by T1 is equal to V1 by V2 whole power gamma minus 1, that is R to the power of gamma minus 1, implies T2 is equal to 300 K into 8 to the power of 1.4 minus 1. We can obtain that T2 also in Kelvin scale, that is the temperature after isentropic compression. He has given that heat supplied is 1500 kilojoule per kg in the process 2 to 3, that is equal to CV into T3 minus T2, implies 1500 is equal to CV of air is given as 0.72, T3 is unknown, minus T2 is calculated above, already calculated, from which we can obtain T3 or maximum temperature in the cycle in Kelvin. The blocks could be easily filled up by knowing the T2, because T2 was already calculated. Substitute the T2 value, we can calculate the T3 also, or T max. Having known T3, we can easily calculate P3 by using Charles' law. Volume remaining constant in the process 2 to 3, P3 by P2 is equal to T3 by T2. Both T3 and T2 are already calculated. Even the P2 is calculated. Therefore, P3 is equal to P max, maximum pressure, is equal to P2 into T3 by T2. All temperature ratios must be in Kelvin scale only. We can calculate P3 also in kilopascal. Having known all the three, that is P2, T3 and T2, having known all the three, we can easily calculate the peak pressure of the cycle in kilopascal. Now, the P4 and T4 are to be calculated at state 4. 3 to 4 is isentropic expansion. That is P3 V3 to the power of 4 is equal to P4 V4 to the power of, P3 V3 to the power of gamma is equal to P4 V4 to the power of gamma. Implies P4 is equal to P3 into V3 by V4 whole power gamma is equal to P3 into V3 is written as V2, because 2 to 3 is constant volume. V4 can be written as V1, because V4 is V1 in the constant volume heat rejection process. That is P3 into 1 by R to the power of gamma. That is P3 is already calculated, 1 by 8 to the power of 1.4. Therefore, P4 could be obtained in kilopascal. Please fill in the blanks, because having known P3, we already calculated P3. And 3 to 4, we can write the isentropic relation, that is T3 by T4 is V4 by V3 whole power gamma minus 1. V4 is V1, V3 is V2, gamma minus 1, R to the power of gamma minus 1. Therefore, T4 is T3 RT max divided by R to the power of gamma minus 1. T3 is already calculated, R value is given. We can calculate T4 in Kelvin. Now, he has asked us to calculate specific work. Specific work means work done per kg, that is equal to thermal efficiency into heat supplied per kg. Thermal efficiency of Otto cycle could be easily calculated as 1 minus 1 by R to the power of gamma minus 1, where R is the compression ratio given as 8. Having obtained thermal efficiency, work done per kg is equal to thermal efficiency into heat supplied is given as 1500 kilojoule per kg, from which you can calculate work done per kg. Now let us consider another problem, objective question, given in gate 02. An ideal air standard Otto cycle has a compression ratio of 5. If the ratio of the specific heats of air is 1.4, then what is the thermal efficiency in percentage of Otto cycle. A 57.5, B 45.7, C 52.5, D 95. The air standard thermal efficiency is function of compression ratio for Otto cycle, that is 1 minus 1 by R to the power of gamma minus 1, where gamma is Cp by Cv, that is given as 1.4 for air. 1 minus 1 by the compression ratio is given as 8.5. Please note that the compression ratio is given as 8.5. It is not 5, it is 8.5. 1 minus 1 by 8.5 to the power of 1.4 minus 1. The answer is 57.5. Now let us consider another problem given in gate 03 regarding Otto cycle. For an engine operating on air standard Otto cycle, the clearance volume is 10% of the swept volume. The specific heat ratio of air is 1.4. The air standard cycle efficiency is A 38.3%, B 39.8%, C 60.2%, D 61.7%. Now let us draw the cycle. One, two, three, four. If we indicate parallelly on a reciprocating IC engine or petrol engine or spark ignition engine, this V2 is Vc, clearance volume. V1 minus V2, this becomes swept volume or stroke volume. The compression ratio R is defined as V1 by V2, which can be written as Vc plus Vs, that is clearance volume for plus swept volume divided by V2, that is equal to the clearance volume. It becomes 1 plus Vs by Vc. This is equal to 1 plus. He has given in the problem that Vc is 0.1 into Vs. Therefore, the ratio Vs by Vc will become 1 by 0.1. Then it becomes the compression ratio is obtained as 11. Then air standard thermal efficiency of Otto cycle is equal to 1 minus 1 by R power gamma minus 1, 1 minus 1 by 11 to the power of 0.4, taking gamma as 1.4. The answer shall be 61.7% air standard thermal efficiency. Now I shall do another problem which was given in gate 2004. The question is given like this. an engine working on air standard Otto cycle has a cylinder diameter of 10 centimeters and stroke length of 15 cm. The ratio of specific heats for air is 1.4. If the clearance volume is 196.3 cc cubic centimeter and the heat supplied per kg of air per cycle is 1800 kilojoule per kg, then work output per cycle per kg of air is A 879.1 kilojoules, B 890.2 kilojoules, C 895.3 kilojoules, D 973.5 kilojoules. The solution to this problem could be given like this. If we draw the cycle on PV plane, 1, 2, 3, 4. Parallel to this cycle, if you draw an engine operating on the Otto cycle, this is VC, this is VS. Now the compression ratio R is obtained as Vc plus Vs by Vc, that is V1 by V2. Now Vc is given as 196.3 cc. We calculate V stroke or swept volume or displacement volume as pi by 4 d square L, that is pi by 4 into diameter is given as 10 into stroke 10 square, and stroke length is 15. So we will obtain V stroke also in cubic centimeters. Therefore compression ratio R is 1 plus Vs by Vc. Once the R is obtained, which falls usually in the range of 7 or 8, the air standard efficiency, thermal efficiency of Otto cycle is 1 minus 1 by R to the power of gamma minus 1. Because heat supplied per kg is given as 1800 kilojoule per kg, implies work done per kg of air is equal to air standard thermal efficiency of air into heat supplied per kg, which may be obtained as 890.2 kilojoules per kg of air. Answer is D. Now let us consider another problem regarding maximum work of Otto cycle. It's a small derivative type problem. given like this. In an air standard Otto cycle, the ambient conditions determine, ambient conditions means atmospheric conditions, ambient conditions determine minimum temperature, which is T1, while the maximum temperature is determined by the design conditions and metallurgical considerations of the piston and cylinder. Because the piston and cylinder material should have to withstand the peak temperatures, that is the maximum temperatures of the cycle as decided by the design conditions. So for fixed values of minimum temperature T1 and maximum temperature T3, they are fixed by the ambient and metallurgical conditions. Find the value of the compression ratio which yields maximum work, that gives, or which gives W max. The solution to this problem is given like this. 1, 2, 3, 4 is Otto cycle. Work done per kg is Qs minus Qr, which holds good for any cycle. That is heat supplied minus heat rejected. Heat supplied is Cv into T3 minus T2 because 2 to 3 is the process of heat supply, minus heat rejected is Cv into T4 minus T1 because heat is rejected in the process 4 to 1. That is Cv into T1 minus T2 minus Cv into T3 minus T4, which can be modified like this by rearranging the terms. That is Cv into T1 1 minus R to the power of gamma minus 1, where R is the compression ratio, plus Cv, taking the T3 common, 1 minus 1 by R to the power of gamma minus 1, because T4 by T3 is 1 by R to the power of gamma minus 1. For maximum work, because work is now a function of compression ratio for a given T1 and T3, differentiating with respect to R, the work function now is differentiated with respect to R, where R is a compression ratio, and equate to 0. That results in minus T1 into gamma minus 1 into R to the power of gamma minus 2 minus T3 into 1 minus gamma into R to the power of minus gamma is equal to 0. This is obtained for maximum work, because work is now a function of compression ratio R for given T1 and T3. T1 is the minimum temperature of this cycle and T3 is the maximum temperature of this cycle. That results in T3 by T1 is equal to R to the power of 2 gamma minus 2, implies R is equal to T3 by T1 whole to the power of 1 by 2 into gamma minus 1. So for a given T3 and T1, this is a condition for maximum work obtained from the Otto cycle. Now let us consider an objective question regarding diesel cycle. In a heat engine working on the diesel cycle A, the compression ratio is the same as that used in the Otto cycle. Option B, fuel is injected into the hot air at high pressure. C, combustion of the fuel occurs at constant pressure. D, option D, air and fuel vapor mixture is drawn into the cylinder during suction stroke. Now if you look at the options that were given here, the compression ratio of diesel cycle would not be the same as that of the Otto cycle, because in the naturally aspirating diesel engine or compression ignition engine, the compression ratios employed are 16 to 22, varying between 16 to 22, whereas the compression ratios of Otto cycles are vary in the range of 5 to 10. So A cannot be the answer. Looking at the B option, fuel is injected into the hot air at high pressure. This seems to be the answer, because in the compression ignition engines or diesel engines that operate on diesel cycle, after compressing the air from atmospheric pressure through high pressures through a compression ratio of 16 to 20, the temperature of the air will increase during the compression. So at the end of the compression, diesel fuel is sprayed into the combustion chamber. Answer is B. Looking at the option C, this is also the answer, because the combustion of the fuel or the heat addition would occur at constant pressure in the diesel cycle. So looking at the fourth option, that is D, air and fuel vapor mixture is drawn into the cylinder during suction stroke. This cannot be the answer, because in the petrol engine or the spark ignition engine that run on Otto cycle, air and fuel vapor mixtures or petrol mixtures are drawn into the cylinder. So the answers here are B and C, whereas D happens in the petrol engines, not in the diesel engines.